Low Performance Input-Output Operations per Second, IOPS. Imagine a highly skilled chef working in a bustling restaurant kitchen. If the waiter hands the chef one massive order for a giant 10-tier wedding cake, the chef can focus all of their energy on that one big job and get it done efficiently. But what if the waiter hands the chef 10,000 individual tickets for single French fries, all at the exact same time? The chef will become completely overwhelmed simply trying to read and organize the tickets, and the kitchen will grind to a total halt. In the world of computer storage, this exact concept is called input-output operations per second, often abbreviated as IOPS. When you are studying for your CompTIA A+ Core 1 exam, you must understand that diagnosing low-performance input-output operations per second is completely different from diagnosing slow sequential transfer speeds. To achieve your perfect score of 900 and to lay a rock-solid foundation for your upcoming Computer Information Systems classes this fall, you absolutely must master how hardware handles thousands of tiny requests simultaneously. Later on, as you pursue your long-term goals in cybersecurity and digital forensics, recognizing this specific storage bottleneck will be essential. When you are conducting a digital forensic investigation on a compromised server, you are not just copying one massive video file. You are using advanced software to simultaneously search millions of microscopic text logs, system files, and registry keys. If the physical storage drive cannot handle a massive amount of IOPS, your time-sensitive investigation will take weeks instead of hours. Let us take a deep technical dive into the physical hardware limitations that cause this specific performance bottleneck. First, we must look at traditional mechanical hard disk drives. A standard mechanical drive spinning at 7,200 revolutions per minute is physically limited to an absolute maximum of around 75 to 150 input-output operations per second. This is a hard physical limit because the metal read and write head literally has to physically swing across the spinning magnetic platter for every single data request. If the operating system asks the mechanical drive to open 10,000 tiny background files at the exact same time, the physical actuator arm simply cannot swing back and forth fast enough. This mechanical limitation causes the drive's internal command queue to fill up instantly, resulting in massive system lag where the entire computer freezes while waiting for the drive to catch up. As an information technology professional, if you see a user trying to run a modern, heavy operating system on a mechanical hard drive, and they are complaining about low performance, your only correct solution is to clone their data and physically upgrade their hardware to a solid-state drive. However, modern solid-state drives and NVMe drives are entirely electronic, meaning they can easily handle hundreds of thousands of operations per second because they have no moving mechanical parts. So why would a modern, expensive solid-state drive suddenly suffer from low input-output performance? The first major cause is severe thermal throttling of the drive's internal controller microchip. NVMe solid-state drives plug directly into the motherboard and process so much data so incredibly quickly that their tiny controller chips generate extreme amounts of heat. If the drive does not have an aluminum heatsink attached to it, or if the computer case has terrible internal airflow, the controller will quickly hit a critical thermal limit. To prevent itself from literally melting, the controller will forcefully slow down its processing speed. When this happens, the IOPS will plummet instantly, and the computer will stutter or freeze during heavy workloads. The second major cause of low performance on a solid-state drive is the total exhaustion of its internal cache memory. Cheaper solid-state drives often lack a dedicated dynamic random access memory chip. This memory chip normally acts as a super-fast digital map, telling the controller exactly where every single microscopic file is located in the flash memory. Without this map, the controller has to constantly search the much slower flash memory just to find the files, which drastically lowers the amount of operations it can perform per second. Furthermore, If a solid-state drive is filled to 99% of its total capacity, the drive loses its fast, single-level cell cache. When the operating system tries to write thousands of tiny files, the drive controller has to perform a heavy read-modify-write cycle for every single file because it has absolutely no empty storage blocks left. This creates massive write amplification, bringing the drive's performance down to an absolute crawl. Finally, you must understand how low input-output operations per sec affect enterprise storage arrays. If a corporate server is running a redundant array of independent disks, or RAID, the hardware controller card manages all of the read and write requests for the entire server rack. These high-end controller cards have their own dedicated memory cache powered by a small lithium battery backup unit. This high-speed cache absorbs thousands of tiny write requests instantly from the operating system and mathematically combines them into one large, highly efficient write operation before sending it to the physical disks. However, if that small battery on the controller card dies from old age, the controller will automatically disable its write cache to prevent catastrophic data loss in the event of a sudden power outage. The exact second that cache is disabled, every single tiny write request has to go directly to the slower physical spinning disks. The server's input-output performance will instantly drop by over 90%, causing massive databases to lock up, virtual machines to freeze, and enterprise applications to crash. To troubleshoot this specific enterprise scenario on your certification exam, you would log into the storage management software, identify the dead battery backup unit warning, power down the server, and physically replace the battery module on the controller card to safely re-enable the high-speed cache. By understanding the massive difference between sequential transfer speeds and random input-output operations, and by knowing exactly how heat, capacity, and cache affect the hardware, you will be perfectly prepared for the most difficult performance troubleshooting questions on your test.